In the hidden realms of our world, a silent war rages. It is a war fought on a microscopic scale, a battle for survival between bacteria and their viral predators, the bacteriophages. Bacteriophages, often shortened to phages, are viruses that infect and kill bacteria. They are incredibly abundant, outnumbering bacteria tenfold. Phages are found everywhere, from soil and water to the human gut. Phages occupy a peculiar space in the biological world. They are not quite alive, lacking the cellular machinery that defines life, yet they possess a genetic blueprint in the form of DNA or RNA enclosed within a protein coat. This genetic material holds the instructions for building new phages. These instructions are put into action when a phage encounters its bacterial prey. The structure of a phage is remarkably simple yet effective. Most phages resemble a lunar lander with an icosahedral head containing its genetic material and a tail equipped with fibers. These tail fibers act as grappling hooks, allowing the phage to attach to specific receptors on the surface of its bacterial host. Once attached, the phage injects its genetic material into the unsuspecting bacterium. The phage DNA or RNA then hijacks the bacterium's cellular machinery, turning it into a virus factory. The bacterium's resources are diverted to produce multiple copies of the phage's genetic material and protein coat. These components assemble into new phages, ready to continue the cycle of infection. The final stage of the phage life cycle is a dramatic one. The newly assembled phages produce an enzyme called endolysin, which breaks down the bacterial cell wall from within. The bacterial cell bursts open, releasing a swarm of new phages into the environment. These phages are now free to seek out and infect other bacteria, perpetuating the cycle. This process, known as the lytic cycle, is a testament to the efficiency of phages as bacterial assassins. The ability of phages to kill bacteria has taken on new significance in recent years. We are facing a growing crisis in the form of antibiotic resistance. Overuse and misuse of antibiotics have fueled the evolution of bacteria that are resistant to these once miracle drugs. These resistant bacteria, often dubbed superbugs, pose a serious threat to human health. The World Health Organization has identified antibiotic resistance as one of the biggest threats to global health. Without effective antibiotics, common infections could once again become deadly. Routine surgeries could become risky endeavors. The very foundation of modern medicine is at stake. Section 4. Phage therapy, a beacon of hope. In the face of this looming crisis, phages offer a glimmer of hope. Phage therapy, the use of phages to treat bacterial infections, is not a new concept. It predates the discovery of antibiotics, with early experiments dating back to the early 20th century. However, the advent of antibiotics, with their broad-spectrum activity, overshadowed phage therapy. Now, with the rise of antibiotic resistance, interest in this forgotten weapon is experiencing a resurgence. Phage therapy offers several advantages over traditional antibiotics. Phages are highly specific in their targets, often infecting only a particular strain of bacteria. This specificity means that phages are less likely to disrupt the body's beneficial bacteria, a common side effect of antibiotics. Furthermore, phages can evolve alongside their bacterial targets, potentially overcoming resistance as it arises. Section 5. Real-life triumphs, phage therapy in action. The potential of phage therapy is not just theoretical, it has been demonstrated in numerous real-life cases. One such case involved a patient in the United States who was suffering from a life-threatening infection in his chest cavity. The infection, caused by a multi-drug resistant bacterium, was unresponsive to all available antibiotics. As a last resort, doctors turned to phage therapy. A cocktail of phages, specifically targeted to the patient's infection, was administered. The results were remarkable. The infection cleared up and the patient made a full recovery. This case, along with others, highlights the potential of phage therapy to tackle even the most challenging infections. It offers hope for a future where antibiotics are no longer our only line of defense against bacterial threats. Section 6. Overcoming obstacles, the path forward for phage therapy. Despite its promise, phage therapy faces significant hurdles before it can become a mainstream treatment option. One of the biggest challenges is the lack of regulatory approval from agencies like the Food and Drug Administration in the United States. Pharmaceutical companies, accustomed to the lengthy and costly process of drug development, have been hesitant to invest in phage therapy. However, the tide may be turning. The urgency of the antibiotic resistance crisis has spurred renewed interest in phage therapy from both researchers and government agencies. Clinical trials are underway to evaluate the safety and efficacy of phage therapy for a range of infections. The results of these trials will be crucial in paving the way for wider acceptance and adoption of this promising approach. The invisible war between phages and bacteria has been raging for millennia. By harnessing the power of these tiny viral predators, we may yet win the fight against antibiotic resistance and secure a healthier future for all.